Right now, at this precise moment, an object older than our solar system is racing through the inner planets at 137,000 miles per hour, outgassing material that should be frozen solid at its distance from the Sun, emitting spectral signatures of metallic nickel vapor where no metal should vaporize, and demonstrating chemical ratios literally never observed in 4.6 billion years of solar system history. And we have exactly 43 days before it vanishes behind the Sunday. Let that sink in. On July 1st, 2025, at 5:15 Universal Time, the Asteroid Terrestrial Impact Last Alert System Telescope in Chile captured 4 frames of what mission controllers initially classified as routine celestial debris. Within 90 minutes, orbital mechanics software at the Minor Planet Center had rejected the preliminary trajectory calculations 17 times. The reason was simple and terrifying. The object designated 3I/Atlas possessed an orbital eccentricity of 6.2. For those unfamiliar with orbital dynamics, anything above 1.0 is physically impossible for a gravitationally bound object. This thing came from outside. This is not speculation. The mathematics are unambiguous. By July 2nd, 31 observatories across 6 continents had contributed 122 independent observations. The Canada, France, Hawaii Telescope, Lowell Discovery Telescope in Arizona, the Deep Random Survey in Chile. Every single data point confirmed the same conclusion. The object approached from approximately 175 degrees inclination to the ecliptic plane, meaning it essentially dropped down through the solar system from above, crossed through the orbital paths of the outer planets, and is now accelerating toward perihelion at 1.4 astronomical units from the Sun, just inside Mars orbit, scheduled for October 30th. The Hubble Space Telescope acquired target lock on July 21st at a range of 277 million miles. What it revealed stops you cold. The images show a distinct teardrop-shaped cocoon of luminous material streaming from a central nucleus, not the diffuse halo you would expect from standard cometary outgassing, a directional plume, jetted. The spectroscopic analysis from the Very Large Telescope in Chile, using both the X-shooter and UVES spectrographs, detected emission lines of neutral nickel atoms glowing in the coma at 3.78 astronomical units from the Sunday. For context, nickel has a vaporization temperature of 2,913 degrees Kelvin. At that distance, solar irradiance generates surface temperatures barely exceeding 150 Kelvin. There is no known natural mechanism that should produce vaporized nickel under those conditions. Here is the terrifying part. The James Webb Space Telescope performed near-infrared spectroscopy on August 6th. The data revealed carbon dioxide, water vapor, carbon monoxide, carbonyl sulfide, and water ice in the coma. Unremarkable chemistry for a comet, except for one number. The ratio of carbon dioxide ice to water ice measured 8:1. The highest ever recorded in any object native to our solar system is approximately 0.3:1. 3I/Atlas exhibits a carbon dioxide concentration 26 times higher than the most extreme case in the Kuiper belt. This is not a comet that formed under conditions remotely similar to ours. This object crystallized in an environment so cold, so volatile rich, so fundamentally alien to our planetary formation models that it forces a complete recalculation of what we thought we understood about protoplanetary disk chemistry. Think of it this way. Imagine you have spent your entire life studying a language. You know every grammatical rule, every syntactic structure, every phoneme. Then someone hands you a sentence in that language, except it contains verb conjugations that do not exist in any known dialect, phonemes your vocal apparatus cannot produce, and a semantic structure that violates the fundamental logic of meaning itself. That is 3I/Atlas. It is speaking a chemical language our solar system never learned. Let me be clear about the institutional response, because this is where the pattern becomes unsettling. On July 3rd, 2 days after discovery, NASA convened an emergency teleconference with the European Space Agency, the Japan Aerospace Exploration Agency, and the Institute for Astronomy at the University of Hawaii. The meeting was not publicized. No press release. The only reason we know it occurred is because of scheduling conflicts that appeared in publicly accessible calendars for the Jet Propulsion Laboratory. Within 72 hours, observation windows on every major space-based telescope were quietly reallocated. Hubble, Webb. The Transiting Exoplanet Survey satellite, which had actually imaged 3I/Atlas as far back as May 7th without anyone noticing, suddenly reprioritized its data analysis queue. On August 7th, NASA and ESA issued a joint statement describing the Hubble observations. Bland, technical, carefully worded to sound routine, but the subtext is screaming, they are not telling you what the models cannot explain. The Transiting Exoplanet Survey satellite data is particularly revealing once you understand what you are looking at. TESS observed 3I/Atlas from May 7th to June 3rd, when the object was 6.4 astronomical units from the Sunday, that is, beyond Jupiter. At that distance, solar radiation intensity is 25 times weaker than at Earth. Standard cometary activity requires proximity to the Sun to initiate sublimation of volatile ices. Yet TESS detected a fully developed coma in early May. The object was already active, already outgassing, already brightening, at a distance where the physics says it should be dormant. Two scenarios explain premature activation at that range. Either the object contains hypervolatile compounds we have never encountered in natural solar system objects, ices with sublimation points so low they react to the faint warmth of distant starlight, or something inside is generating heat. I want to be absolutely clear. I am not suggesting artificial origin. I am stating an observational fact that currently lacks a satisfactory natural explanation. There is a difference. The first is conspiracy. The second is science. Let us construct 3 hypothetical scenarios and evaluate them against the data. Scenario Alpha. Benign natural object. 3I/Atlas is a primordial comet ejected from a planetary system orbiting a red dwarf star. Red dwarfs are cooler and dimmer than our Sunday. The planet-forming material around them would be significantly colder, potentially allowing carbon dioxide to dominate water ice in the condensation sequence. The extreme carbon dioxide to water ratio becomes explicable. The early activity at 6.4 AU could result from carbon dioxide ice, which sublimates at 194 Kelvin, far below the sublimation point of water ice at 273 Kelvin. The nickel emission requires more creativity. Perhaps the object collided with metallic debris in interstellar space, embedding micron-scale nickel grains in its surface matrix. Solar wind sputtering and micrometeorite impacts could liberate those atoms into the coma, where solar UV photons excite them to emission. This scenario requires multiple low probability events, but remains within the boundaries of known physics. Scenario Beta. Planetary system diagnostic or warning. Some astrophysicists have begun suggesting that 3I/Atlas may be a fragment of a disrupted exoplanet or dwarf planet that experienced catastrophic breakup. If the parent body had differentiated, developed a metallic core, and subsequently shattered due to tidal forces during a close stellar encounter or planetary migration event, the resulting fragments could carry both primitive icy mantles and core material. The nickel emission becomes a signature of that core. The carbon dioxide enrichment reflects formation in the outermost regions of that system before ejection. Under this model, 3I/Atlas is not a messenger. It is evidence of violence, a tombstone marking the destruction of a world that once existed. The early activity suggests the breakup was recent on cosmic timescales, within the last 100 million years, leaving the interior still thermally active from the energy of fragmentation. If this scenario is correct, We are not looking at a pristine sample of planet formation. We are looking at wreckage. Scenario Gamma, technological artifact or probe, undergoing operational changes. I include this not because I endorse it, but because excluding it without examination would be intellectually dishonest. If an advanced civilization sought to study other stellar systems without mounting expensive interstellar missions, you would design small, durable probes capable of long-duration transit through the interstellar medium. You would construct them from materials abundant in cometary bodies to provide natural camouflage. You would equip them with radioisotope thermal generators or other compact power sources to survive the cold of interstellar space. As the probe approaches a star system of interest, it initiates observation protocols. The internal heat source, no longer needed for survival, begins venting waste heat. The carbon dioxide and water vapor are not outgassing, they are coolant. The nickel emission is not contamination. It is a spectral signature from onboard systems that were never designed to be scrutinized by spectroscopy. The directional plume captured by Hubble is not random outgassing. It is a propulsion adjustment. Under this model, the early activation at 6.4 AU is not premature. It is right on schedule. The probe has arrived and is beginning its mission. This third scenario sounds absurd. I know that. The problem is the improbability stack. Each individual anomaly, taken in isolation, can be explained naturally with sufficient creativity. Extreme carbon dioxide ratio, possible under red dwarf formation conditions. Early activation beyond Jupiter, carbon dioxide ice volatility, nickel emission, micrometeorite contamination, directional outgassing plume, rotating nucleus with active regions. None of these is individually impossible. But when you stack them together, when you calculate the joint probability of all these low probability explanations occurring simultaneously in the same object, the numbers become uncomfortable. Let me quantify this. Estimates for the spatial density of interstellar objects with radii greater than or equal to 3, I/Atlas, are approximately 10 to the negative third per cubic astronomical unit. That is one object per 1,000 cubic AU of space. The Vera C. Rubin Observatory, which came online this summer, projects detecting 1 to 2 interstellar objects per year once it reaches full operational capacity. That gives us a baseline detection rate. Now consider that 3I/Atlas is only the third confirmed interstellar object ever observed. The first one, I/Oumuamua, in October 2017, exhibited extreme elongation, at least 10 to 1 length to width ratio, and non-gravitational acceleration that could not be explained by standard cometary outgassing because no outgassing was detected. The second, 2I/Borisov in August 2019, behaved like a normal comet, icy nucleus, visible coma, carbon monoxide production rate of 1.2 times 10 to the 24th molecules per second, dust production around 4 kilograms per second. Boring, predictable. 3I/Atlas breaks the pattern again. Different chemistry, different behavior, different everything. The pattern itself is the anomaly. 3 interstellar objects. 2 of them exhibit properties unlike anything in our solar system. That is a 66% outlier rate. If interstellar objects were a representative sample of galactic planetary system debris, we would expect them to follow similar distributions to local objects. We do not observe that. We observe a strange bimodal distribution, normal comets like Borisov, and deeply weird objects like Oumuamua and 3I/Atlas. Now add the timing. Oumuamua was discovered after it had already passed perihelion and was leaving the solar system. We missed the close approach. Borisov was discovered 3 months before perihelion, giving us a 1-year observation window. 3I/Atlas was discovered 4 months before perihelion. currently at 2.8 AU inbound, brightening steadily, and will remain observable until late September before solar conjunction renders it invisible from Earth. Then it re-emerges in early December on the outbound leg, passing within 1.83 AU of Earth on December 19th. The observation windows are getting longer. Either our detection capabilities are improving, which they are, or the objects are becoming brighter earlier, which suggests they are becoming more active. If you follow the evidence dispassionately, you are forced to ask uncomfortable questions. The immediate observation priorities are clear. NASA's Juno spacecraft, currently orbiting Jupiter, will attempt observations in March 2026, when 3I/Atlas passes approximately 0.31 AU from Jupiter. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter acquired imagery on October 3rd, when the comet passed 30 million kilometers from Mars, close enough for the high-resolution stereo camera and color and stereo surface imaging system to resolve structural details. The instruments also attempted spectroscopy using the Omega, SpyCam, and Nomad spectrometers, though preliminary reports suggest the signal-to-noise ratio was marginal. The European Space Agency's Jupiter Icy Moons Explorer, currently en route to the Jovian system, will observe 3I/Atlas in November using multiple instruments, including cameras, spectrometers, and particle sensors. Data will not return until February 2026 due to telemetry limitations and current spacecraft orientation using the high-gain antenna as a solar heat shield. Here is what we need to watch for in the coming months. First, trajectory deviations. Any alteration to the predicted orbital path that cannot be explained by gravitational perturbations from known masses. Standard comets exhibit non-gravitational acceleration due to outgassing thrust, typically on the order of 10 to the negative 8 AU per day squared. If 3I/Atlas demonstrates acceleration an order of magnitude higher, or worse, demonstrates vector changes inconsistent with the Sun-comet geometry, we have a problem. The orbit integrations are being continuously refined by the Minor Planet Center. Any anomalies will be immediately apparent. Second, activity pattern changes post-perihelion. Comets typically show peak activity near perihelion and gradual decline as they recede. If 3I/Atlas maintains brightness or increases activity after perihelion on October 30th, it violates standard volatile sublimation models. The test data already showed it was active far earlier than expected. If it stays active far longer, the hypothesis of internal heat source becomes unavoidable. Third, spectroscopic evolution. The James Webb Space Telescope has scheduled follow-up observations in December after the object re-emerges from solar conjunction. If the chemical composition of the coma changes significantly between August and December, beyond what thermal models predict from heliocentric distance variations, it suggests complex internal processes, layered volatile composition, subsurface reservoirs being exposed, or operational phase transitions. Fourth, structural fragmentation. 2I/Borisov broke apart in March 2020. Hubble captured the nucleus elongating and splitting into at least two distinct pieces. Comets fragment due to thermal stress, rotational instability, or structural weakness. If 3I/Atlas fragments, we get to see what is inside. If it does not fragment, despite undergoing perihelion stresses, it suggests unusual structural integrity. Fifth, non-gravitational acceleration direction. This is critical. Cometary outgassing produces thrust in the direction opposite the sublimating surface. For a rotating nucleus with active regions, the thrust vector averages out based on rotation period and geometry. If 3I/Atlas exhibits sustained non-gravitational acceleration in a direction inconsistent with its rotation and solar geometry, you cannot explain it with outgassing. 1I/Oumuamua showed this. The acceleration vector did not align with the Sun-comet direction. it pointed slightly off axis. That single fact has generated more papers and more controversy than any other aspect of the object. The timeline is unforgiving. Perihelion occurs October 30th at 1.4 astronomical units. The object will be unobservable from Earth due to low solar elongation from late September through late November. The Earth-based observation window closes in 43 days. After that, we are flying blind for 8 weeks. When 3I/Atlas re-emerges in December, it will be outbound, receding at 61 kilometers per second, hyperbolic excess velocity, identical to its inbound speed because hyperbolic orbits conserve energy. Every day of delay costs us resolution, photon count, and signal strength. The object will cross Neptune's orbit in June 2024. After that, even Hubble cannot track it. The window for comprehensive characterization is November 2025 through March 2026. Then it is gone, forever. This is why the Vera C. Rubin Observatory matters so much. Starting next year, it will survey the entire visible southern sky every few nights using an 8.4 meter primary mirror and a 3.2 gigapixel camera. The legacy survey of space and time will generate approximately 15 petabytes of data per year. The survey will detect an estimated 100,000 near-Earth objects, 40,000 Kuiper Belt objects, and potentially 15 to 70 interstellar objects per decade, depending on whose population models you believe. With that detection rate, we transition from studying individual curiosities to building statistical samples. We can characterize the population distributions. We can determine if objects like Oumuamua and 3I/Atlas are rare outliers or representative of a distinct class. We can test formation models against observational data instead of theoretical extrapolation. But that is future tense. Right now, we have one object, a closing observation window, and a stack of unexplained measurements. I keep returning to the institutional silence because it bothers me. In 2017, when Oumuamua was discovered, the scientific community engaged in open, vigorous public debate. Avi Loeb from Harvard published papers suggesting artificial origin and went on every media platform that would have him. Other scientists published rebuttals. It was messy, loud, transparent. With 3I/Atlas, the discussion is muted. Technical papers on RXIV, dry press releases, no controversy, no speculation, just data. Two possibilities explain this. Either the scientific community learned from the Oumuamua media circus and is waiting for comprehensive data before making public statements, or the preliminary findings are strange enough that no one wants to be the first to say it out loud. You cannot have it both ways. Either the anomalies are explainable and routine, in which case why the observation frenzy and schedule reshuffling, or the anomalies are genuinely puzzling, in which case the silence is deafening. Let me walk you through one more data point that has not received enough attention: the kinematic age analysis. When you trace 3I/Atlas backward through galactic space using proper motion vectors, accounting for the gravitational potential of the Milky Way disk and bulge, you can estimate when the object was last gravitationally bound to a stellar system. The preliminary analysis, published in August by researchers at the University of Michigan and Michigan State, suggests 3I/Atlas may be significantly older than our solar system. Not millions of years, billions. If that age estimate holds, this object has been drifting through interstellar space since before the sun ignited. It is a fossil, a relic, a sample of galactic chemistry from an era when stellar populations and planet formation physics were different from today. That makes it invaluable for understanding galactic chemical evolution. It also makes the nickel emission and extreme carbon dioxide ratio even harder to explain. Cosmic ray exposure over billions of years should erode surface composition, not preserve it. The object should be radiation darkened, chemically altered, structurally weakened. Instead, It is pristine enough to generate spectral emission lines and demonstrate active volatile sublimation. Consider the implications. An object billions of years old, traversing the galaxy at 61 kilometers per second, intercepts our solar system at a time when humanity has just developed the technology to detect and characterize it. The anthropic selection effect is obvious. We only detect what we have the tools to detect. But the timing remains striking. If 3I/Atlas had arrived a decade earlier, Pan-STARRS might have missed it. If it had arrived a decade later, Rubin Observatory would have detected it months earlier, tripling our observation window. Instead, it arrives precisely when our capabilities are advanced enough to detect it, but limited enough to make comprehensive study difficult. I am not suggesting design. I am noting coincidence and allowing you to decide what, if anything, it means. The December re-emergence will be critical. Now, if you want to follow this in real time, here is what to watch. First, the Minor Planet Center publishes orbital elements daily for active objects. Any updates to 3I/Atlas trajectory will appear there. Second, NASA and ESA image archives. Hubble, Webb, and other assets upload processed data to public servers, usually with a delay of weeks to months, but sometimes immediately for objects of high interest. Third, the astronomer's telegram. Professional astronomers use this to announce transient events and observations. If something significant happens, it will appear there before any press release. Fourth, RxIV preprint server. Scientific papers get posted there before peer review. If a major discovery is made, you will see it on RxIV first. To stay on the timeline as this unfolds, consider subscribing to channels that monitor these sources. The data is public. The tools are accessible. You do not need a PhD to track orbital elements or download telescope images. The democratization of astronomy means you can watch this investigation happen in real time instead of reading about it in summary 3 years later. And here is the question I want you to think about while you are watching. When you look at all the data together, the extreme carbon dioxide ratio, the early activation, the nickel emission, the directional outgassing, the hypervelocity transit through the solar system, the kinematic age implying billions of years of drift, do you see a comet? Or do you see something that looks like a comet? Because those are not the same thing. In planetary defense circles, there is a concept called strategic ambiguity. The idea is that if you detect something genuinely anomalous, something that might require societal response, you do not immediately announce it to the public because you do not yet understand it well enough to provide context. You gather data quietly, you run models, you consult specialists, you build consensus. Then, when you have enough information to frame the discovery properly, you go public. The risk is that premature disclosure causes panic or misinterpretation. The cost is that people notice the silence and interpret it as cover-up. I do not know which side of that line we are on with 3I/Atlas. I genuinely do not. The data is public. The observations are real. The anomalies are documented. But the synthesis, the big picture interpretation, remains unspoken. So let me ask the question directly. Is this contact? Or is it pattern seeking? Are we seeing evidence of an interstellar probe designed to study star systems and their planets, specifically timing its activation to coincide with detectable observation as a form of graduated disclosure? Or are we seeing a primordial comet fragment from a disrupted exoplanetary system that happens to have unusual chemistry because it formed under conditions we have not yet fully modelled? Both explanations fit the data if you squint hard enough. One requires exotic natural processes, one requires intelligence. Historically, when faced with this choice, the universe has always resolved in favour of the natural explanation. Always, without exception. From canals on Mars to pulsars misidentified as alien beacons, every seemingly artificial signal has turned out to be nature doing something we had not imagined. But here is the thing about precedent. It holds until it does not. 3I/Atlas is currently inbound at 378,000 kilometers from the Sun per day. In 43 days, it drops below the observational horizon. In 60 days, it reaches perihelion. In 90 days, it re-emerges. In 6 months, it is gone. We have one chance to get this right. Are we alone? That question echoes through every telescope pointed at 3I/Atlas. It echoes through every spectroscopic analysis. It echoes through every orbital calculation. Not because the data says we are not alone, but because for the first time in history, the data refuses to definitively say that we are. And that, more than anything else, is what keeps me watching the sky.